Hi, my name is Will Billows. This is Physics 1, and I will be doing Lab 3, Mass of a Black Hole. So the purpose of this lab is to model a black hole's mass based on a star orbiting around it, and we are also calculating the velocity of a ship orbiting around a planet and seeing if we are successfully able to orbit around both a planet and the moon around it. So here's a preview of results. The average mass of the black hole was found to be 7.541 times 10 to the 43, and the ship's orbit was successful. We were able to orbit around both the planet and the moon orbiting around it. So the fundamental theorems, we have F net perp is mv squared over r times n hat. Then we have F net parallel is dp dt times p hat. And universal gravity is negative gmm over r squared times r hat. And the velocity update is vi plus f net over m times delta t. So we combine universal gravitation, Newton's second law, and parallel and perpendicular forces to calculate these. So the assumption that I made is we have a finite time step, so there will be some numerical error in calculating the mass of the black hole. So if we average the mass of all of them, then we are able to account for this numerical error and find the actual mass of the black hole. So here are some possible errors and initial conditions. It is all computational, so no conclusions can really be drawn from this experiment, but the only possible error could be that there was some sort of error in the code, which there's not, so it's decent. And then the initial conditions are that gravity, of course, is the gravitational constant. We have the mass of the star, delta t, and time equals 0. Then for the initial condition of the ship, I found that negative 24,600, y value 25,500, and then z value 0 created a good orbit. Now here's the code. And as we can see here, we have the star orbiting around the black hole. And here I have, I computed initial final momentum vectors. I calculated the change in velocity and change in momentum. I calculated dp dt, and then I found f net, and then I found p hat, the magnitude of dp dt, and the parallel and perpendicular forces. And the results are, by averaging the values, I was able to compute the mass of the black hole at 7.541 times 10 to the 43. So the code for part 2, I computed the force on the moon, and then I found the net force on the spaceship, and then I applied Newton's second law and the position update formula in order to make it orbit around the moon and the planet. So the results of part 2, I was able to get a successful orbit based on the gravitational attraction of both the planet and the moon, and it didn't crash after the time interval, so I would say it is pretty successful. So what does this mean? We have net force versus the rate of change of momentum. So net force is directly related to acceleration, while the rate of change considers both mass and velocity changes. The perpendicular component of force changes the direction of momentum, while the parallel component changes the magnitude, speed. And the momentum depends on mass and velocity, while force depends on interactions, meaning force can exist even if momentum isn't changing, which balanced forces include. So what if, and this is for part 2, the computational model of a multi-body system where we're including not just 3 bodies, but we're also including maybe a black hole, a star. So the model must include gravitational interactions between all bodies. So the black hole, the star. So the star would orbit around the black hole. The planet would orbit around the star, and the moon would orbit around the planet, and the ship would orbit around all of these, so it would be a much more confusing computational model. So we would have to use Newton's law of gravitation. So the dominant interaction would be black hole's gravity, followed by the star's gravity, with smaller contributions from the planet and the moon affecting the orbit of the spaceship. And the system should count for relativistic effects if precision is necessary, especially near the black hole.